All right, so next I'll introduce Ruben, so another entity from the now famous, I guess, Dagstool seminar. So it's almost like a Dagstool reunion here, I would say, but Ruben, take it away.
Okay, thank you. So good afternoon, everyone. I think the title is kind of self-explanatory. We're going to talk about Ansible and how it's probably Turing complete. I should qualify this as probably. I'm not going to formally prove anything. But I'm going to show you some code examples and tell you why it probably is. But first off, I'm going to show you how Ansible should actually be used in practice, how you would typically write actual Ansible code. So that's a file on the left, a playbook. And there's a couple of tasks in there. So you have, I don't know if my pointer actually works on this one. Let me check. Oh, okay. So you've got like 3 tasks here, right? First one, install some packages in Python. There's the package action, which is, I mean, you can kind of think of these as function calls, right? So you're calling the package function with a name and a state, and the name actually indicates which packages that you want to install. There's some other pip action that installs some pip packages. And basically for each of these steps, they're executed in order, and Ansible is going to execute them on all of the machines in some infrastructure or some cluster that you have. So basically you can configure like actual machines with this language. Of course, I'm calling it a language. It can be used for configuration management, for automation, for infrastructure as code, but it's not a programming language, or at least that's what Ansible wants you to think. This is a tweet from 2019, so yes, it's still a tweet, not an X or whatever it's called. I think this guy is like some PR person for Ansible, and he's really shouting at us like it's not a programming language, it's just automation, right? Then this guy replies, well, what distinguishes it from a programming language? It has programming language constructs such as variables, for loops, conditions, do whiles, exception handling, etc. I haven't seen any proof that it's Turing complete, but I wouldn't be surprised. And well, 4 years later, now I'm here, which, I mean, I'm not going to show you a proof, but I'm going to give you the intuition why it probably is. Now, before I can go into that, I have to explain some of the language features that we'll need to actually interpret these code examples, starting with variables and expressions. So here we have one task, which is going to debug some message to the screen. And the message is a string. There's a template expression in there between the double braces saying x plus y. X plus y are references to variables which are defined at the bottom. And pretty much this is going to do 10 plus 15, 25, right? Special about Ansible is that there's a lot of different ways that you can define variables. I'm not going to introduce all of them. I did that 2 years ago at CONFLANG the first time. There's 22 different ways. We're only going to be looking at one. And expressions are also a bit weird in that they're lazily evaluated and can lead to some other issues. Again, not really the point of today. Secondly, there are also dynamic variable definitions. These are the ones that we're actually going to need. So we have a set fact. It's an action which takes the names of variables as arguments and then expressions that define the value that those variables need to have. And then you can dynamically define these variables. So in this case, again, we're going to define a variable called result. We're going to evaluate this expression. Is going to be 25, the string 25, not the number, the string, because again, these things are template literals or template expressions that are embedded in strings. And then later again we can define, we can print the result of this definition. This variable is now a global variable, it's defined in a global scope. And again, the sum is going to be 25. So that's not all. There's also conditionals. So you can conditionally do certain things. For instance, you can check in a conditional with this when colon construct that the result is even or odd. And if it is even, you're going to print the sum is even. If it's not even, the task is going to be skipped entirely. Nothing is going to be printed to the screen. Of course, you can also dynamically, conditionally define variables with set fact, but not really too relevant right now. However, there's a final thing that I need you to understand today. It's include tasks. This is dynamic inclusion of a file that includes some of these steps of these tasks that can be used to modularize these tasks. So again, we have the same example as previously, but now we are dispatching from another file, including this dynamically. And when I say including this dynamically, I really mean it's entirely dynamic. So it's going to execute every task up until this point, and then only then it's going to parse the file and actually load in all of these tasks, execute the tasks, etc. You can also put conditionals on them. And one thing that is it's used for sometimes is that the file name that you're including is going to be parameterized by an expression. For instance, you have install underscore and then the operating system family name, so you might have different tasks for a Red Hat operating system or a Debian one, etc. Now, if you can do if you can do dynamic task includes, what is stopping you from doing recursive task includes? What if a file includes itself? Like in this example, you have at the bottom an inclusion of the file itself, and then of course it's going to include itself, and it's going to do that again and again and again and again and again and again and again, right? And it's never going to stop. Actually, Ansible is implemented in such a way that this is not going to lead to a Stack Overflow, so this will indeed run forever, pretty much. Now, fortunately for us, we can do conditional inclusion, meaning we can put a bound on the inclusion of this file. So we can, for instance, in this case, we're printing a message that we're going to decrement x. We're going to use setFact to dynamically define x as x minus 1. We actually have to cast x to an int because, again, it's a string. And if x is not 0, we're going to include ourselves again. If x is 0, we're going to skip this part, and then we can print that x is 0. And if you run this, you can actually see at the very end here, this thing is skipped. So this is where the loop stops, right? And so now you have created a recursive loop where you're decrementing x all over again. And that pretty much opens up a whole can of worms, because if you can do this, you can also write a factorial, right? You can do an iterative factorial where you're dynamically defining a result, which is pretty much your current result. If there's no current result, we're going to use a default of 1, and then we're going to multiply that by n, at the same time also decrementing n, as long as n, of course, is not 0. Once n is 0, then we can stop. If n is not 0, we're going to loop again, and, well, that's your factorial. So here you've implemented a recursive or an iterative factorial via recursive inclusion in a language that is not a programming language. Now, of course, you can go further. You can also do Fibonacci. It's a bit more complicated. So basically, we're going to be using a stack here. The reason why is because Ansible variables cannot be defined in terms of itself. So you have to store, like, unless you use setFact, but that, of course, overrides the previous value. So you need to store these values somewhere on a stack. So we're doing kind of stack-based programming. And then we have our recursive Fibonacci, which, well, to calculate the Fibonacci of n minus 2, you have to push something on the stack, rather like actually your previous result. And then pretty much it's a Fibonacci, right? It's just recursively calling itself over and over again. It's actually looping between these two files up until the point that your base case is reached where n is 1 or 0. And again, we need this stack for the the Ansible semantics of not being able to actually define a variable in terms of itself. So, okay, we can do factorials, we can do Fibonacci, that's all nice and all, but can we do more? Can we do something stupid? And yes, we can. We can write a scheme interpreter in Ansible. This QR code takes you to a GitHub repository. It is a limited subset of scheme, but it supports closures, higher order functions, recursion, apparently also concells if you implement your concells yourself. I haven't bothered with it, but this guy over there, Bram, he submitted a pull request 2 days ago to show that it also works. I'm not going to show you exactly that it works, just trust me on this. I haven't prepared for a demo, but maybe later. But I'm going to highlight some of the things of the implementation of this scheme interpreter. So, according to Coen, the most important part of a scheme interpreter is lambda expressions and closures and function applications. So if we encounter a lambda expression, we can create a record. The record is a type value, so the type of the record is a value, it stores a value. The data type of that value is a closure, and then the closure has 3 properties, namely the parameters, which are the formal parameters of your lambda, of course. You have the body of the lambda and, of course, an environment, otherwise you cannot have a closure. So now we've created a closure record in our Ansible scheme interpreter using this setFact construct. And then when we need to evaluate a call expression, I'm not showing you how we detect call expressions. We have an entire parser implementation for scheme in the Ansible interpreter as well. I really don't want to explain this one. But maybe during the break. Yeah, actually I do. Like, this was a weekend project, by the way, right? I mean, it's not like funded by anyone. But first, of course, we evaluate our arguments, recursive call to, I mean, eventually it recursively does some evaluation and you can get your results. You push those results on a stack again, because stack-based programming. You have to evaluate the operands. Could be a lambda, could be a name, could be anything. We're going to assume that it is a lambda, or rather a closure. Could also be a built-in that's handled separately. And then finally we dispatch based on the type of our callee, which we hope is, of course, a closure. And then when we do that, we need to call this closure, of course, as we all know from the Structure and Interpretation of Computer Programs book. We need to extend our environment. We need to create a new local environment with a parent environment. The parent environment is, of course, the definition environment of the closure. And we have to bind our formal parameters to the actual arguments that have been given in the call that we just evaluated. Then we can recursively evaluate the body of the lambda in this environment and then finally destroy it. And we have done our function application, all in a language that is not a programming language. Now, of course, it's not trivial. There are some challenges, or why you should not do this. As I mentioned already, Ansible thinks everything is a string because template expressions are strings, so we need to do a lot of casting. The entire thing is filled with casting to int. There are complicated variable semantics. As I mentioned previously, there's 22 different rules in which you can define variables. They have very weird semantics that we need to kind of struggle with. I'm an opponent of the set fact construct, but this is the only way you can actually do it. And then finally, there's also, I mean, they have conditionals, but they don't have else branches in those conditionals. So either you need to specify a conditional and invert it every time that you write another task, because otherwise it's just going to fall through, or you do some weird, ugly dispatching based on the dynamically constructed file names to do include tasks. So those are the challenges, so please do not do this. On the other hand, please, PRs are welcome. There are some limitations. We are missing a lot of built-ins. There's no const cells. I don't think we even have a division right now. There's, of course, I mean, Scheme is known for let bindings. We don't really support many of those, if any, I think, but that was not the point. Mutability is also something that we're currently still missing, but it is work in progress, but I just didn't find much time anymore. Garbage collection, if anyone dares, and for the real crazy people, there's call with current continuation, which again I don't really recommend. Now, thank you to reviewer B of CONFLANG, who wanted a proper proof that that Ansible is Turing complete by simulating a Turing machine. I hope that I've given you the concepts to implement this yourself. Again, the GitHub repository is public. You can create pull requests if you wish. Now, you might be thinking, okay, this guy is crazy. Fair. But also, I mean, yeah, sure, Ansible is Turing complete, so what? Right? Does it really matter? Now, there are a couple of questions that I, in my own research, want to answer, like, does this Ansible script contain some security vulnerabilities? Will the configuration that is being deployed by this Ansible script be correct? Might there be any variables that are not defined in this Ansible script, or even does it terminate? Because this question, especially the last one, is generally undecidable now that we know that we can actually recurse. On the other hand, we've also done mining software repository studies with some of these tools that we've created. On 25,000 GitHub repositories that use Ansible, there's only one single repository which didn't terminate, or might not terminate, which did these recursive includes. That was probably even a bug, so I don't think this was really intentional. Now, so what? Oh, good question. Now I'm going to end with some food for thought. First off, okay, we have these recursive task inclusions. I don't think it's by design. I think it's very much accidental. Should we prevent this in Ansible itself? Is it worth the effort of preventing people from doing this so that your language is not Turing complete? And on the same topic, is there any value in your configuration management language being Turing complete? I would like to hear your thoughts on that. Now, if you can write a scheme interpreter in this language, I think that is a sign that your language is too complicated. Especially if it takes me this much effort to do so. And of course, Ansible takes a lot of inspiration from proper programming languages. You have your variables, your expressions, do whiles, loops, conditionals, etc. why bother with the DSL? Why bother using YAML with some special semantics? Why just not use Python with function calls and provide some library of functions, kind of what Daniel is probably going to be talking about later, Pulumi, etc. And then finally also, okay, why not embrace these programming languages, but at the same time, Ansible scripts lack a lot of common language features. We need to use stacks to do all of these things. There's no function calling mechanisms. Should there be functions in Ansible to make my life easier? So those are my final questions. Would love to hear some discussion on that, and other than that, thank you.
Yes, thank you, Ruben. Any questions? Jan.
So just as partial, at least, ideas about Turing completeness, I think that in general it might be a bit overrated. I mean, the question of Turing completeness and decidability in practice are not always exactly what we think. For example, DAL is not Turing complete, but you can encode a command function, so it doesn't give you any bound on the running time of your program. But it does prevent stupid errors, and that is something that is interesting because, for example, in Nix, finite recursion is something you encounter often because it's a complex fixed points. And so I think that Turing completeness in itself is not truly an interesting property to discuss. You can discuss if your thing can terminate in a finite time or in a reasonable time, or maybe in Q, for example, this gives you decidable analysis on some property of the language. And those are interesting property, but I don't think Turing completeness per se is more of a branding for I mean, there is a blog post by Gabriela Gonzalez, the author of DAL, about that, and she herself tells something like that it's more like a part of a nice property, but more than a branding itself. And for Turing completeness, Nickel is Turing complete, and we did that because, at least in part in Nix, you need sometimes to parse things like very simple file format, but still, I'm not talking about parsing bash, but still handle structured data in a recursive way. And even if it might be doable in something expressive like DAL, it's just a huge pain. So we try to provide the basic combinator so that you don't need recursion when you don't have to, like maps and whatever non-Turing complete language provide. But it seems like for something it's just way simpler to not be Turing complete. That's my stance.
Thoughts on Turing completeness. I would definitely agree with you that it's probably overrated. And for example, if you know exactly what your configuration is, there's relatively little value in Turing completeness, because if you have, for example, an infinite loop, you're not going to wait forever. But if it takes too long, you're going to rewrite your code. You give yourself a bound how much time you can spend executing this thing, and you're going to write your configuration. You're going to fit in the bound. I think the question becomes more interesting when you consider compositionality, because if you do not know exactly what the configuration is, you have multiple sorts of configurations which have been independently tested by different people in different environments. I think it's quite nice to have some sort of guarantees what happens when you put those things together in a system that might not be, it might run as a sort of a batch job or something that's not even observable. Although also, as you said, that doesn't necessarily mean there's any sort of a useful bound on how long that would take to execute. But so it's still up for debate. But yeah.
Just one comment on there. So Carpenter's book on feature structure shows a really nice example where you have two obviously non-recursive graphs that if you combine them together become infinite. So that is possible, that kind of stuff. Yeah.
Have you seen people using the Python API of Ansible on FES to do what?
Personally, not really, not that I know. So I don't even really know of a Python API to Ansible. I know that there's you have a command line interface, and I'm assuming that people can also write their own scripts and possibly import Python. Actually, wait, no, what am I saying? Of course, I've used the Python API of Ansible in my own projects. I use Ansible to parse Ansible, or rather the interpreter itself, not Ansible code. I'm not that crazy. And of course, there's also a lot of people actually write Python plugins for Ansible, right? So it's the whole kind of concept behind the new collections thing. So for instance, if there's like AWS machines that need to be managed there in the AWS collection, that's just a bunch of Python files where people can write proper programming code. And then make it possible for us to just write normal tasks that like execute some action. So that definitely happens.
But no one includes Python.
Possibly, I'm not entirely sure. I can't really give an answer to that.
There are definitely people writing configuration in Python, but yeah.
If I'm not mistaken, Facebook doesn't have a configuration language, and they're writing all the configs in PHP. So probably that's one of the solutions for this problem. I just want to make a comment that you can treat the configs as a DSL for your application. Basically, you are telling application what to do in a very specific way. Mm-hmm. And surprisingly, to your point that should we use a proper programming languages, like this particular resolution of the problem will not get rid of DSL. So people will still need DSL and still want to use DSL because they want to kind of create a situation when they don't need to think about a reason about the whole program. They want to reason about a small portion of it. And I know one language which actually embraced it. Mm-hmm. And the language is Scala. And I wrote in Scala and I still survived. The problem with Scala is that their type system is Turing complete. So when you're creating a type in Scala, you can actually have a chance to emulate Turing complete system. And their build system is actually Scala as well, SBT. Mm-hmm. You don't want to use it. It's not very pleasant experience, but well, it's possible. Yes, people can do that, and people can survive.
I think on the level of like configuration of a binary or something, definitely people are writing configurations in different languages. What I was really meaning with this last point is like if we go back to an actual proper example of Ansible code, this one, like in a sense, like this package thing is just okay. Call a package function with the name borksys packages or something and the state present. These are just function calls to functions of which you don't see the code, but then in the backend it's just Python pretty much. Technically, you could probably just import these Python functions into an actual proper Python file and then use proper language semantics to use variables and expressions without all of the Ansible cruft around it. So maybe we should like really on the level of machine configuration. Instead of like single software configuration, that was more the point here, if that makes sense.
Okay, thank you. So if there's more questions, we have a Q&A session